Now we are going to check out the resistance, and the resistance is just like it is in electricity. It slows the flow, so let's add that. And that means that your fluids slow down when there's more resistance. It's just basically caused by friction, which is something that we haven't talked about a lot, but I know many of you are very familiar with. And it's caused by the surface of the container and the fluid touching. We need to take a look specifically what types of things create the largest resistance. One thing that creates a lot of resistance is the shape of the container or the pipe that it's flowing through. So very sharp turns, like 90 degrees, make it flow a lot slower. And this is just like when you're driving, and I know many of you don't, but you have to slow down in order to make it through turns. If you didn't, you would go flying off into the ditch. So that is the example that we have here. Traffic will slow down when you end up hitting a curve. It speeds up on straightaways because you're not worried about flying off. If you want to reduce the amount of resistance, you make the path as straight and wide as possible. The size of it, the width, is actually the other thing. So there are two things that affect resistance. One being the number of bends. The second thing being the actual width. The width or cross-sectional area of the container or pipe that your fluid is flowing through is the other thing that's going to affect how fast it's going. Velocity, as you saw in your question over here, it asks you about velocity. That is nerd for the word speed. So every time you hear the word velocity, we're just talking about speed. We'll talk about this next year. We'll do velocity a lot. Cross-sectional area is nerd for diameter, which is how far across a pipe, or the width of a pipe, okay? Here is the point. The larger the cross-sectional area, so the larger pipe you have, the slower the velocity, okay? And that's what we need to take away from this. You will also have less resistance, I think. Oops, sorry. So, taking those two things into mind, I want to actually make those notes up here. Resistance depends. 1, the shape of the path. And 2, the size of the path. All right? And that's going to be the two things that are going to affect it. That's going to affect our resistance. So, very quickly, I'd like to highlight this, and we're going to use this in order to answer these next two questions. So let's keep those two things in mind as we look. Number 6 is asking us, there are two locations where the water moves with the same velocity. So, we also have the y in there. We want to make sure we can answer y. Again, the bigger the cross-sectional area, the slower the velocity. If we have the same velocity, that means that we must have the same size, okay? And don't think that the shape is going to matter here because this is straight. If you notice, it does get skinnier here in the middle. If you have ever played with a hose, when you decrease the size of the hose, it increases the speed that the water comes out. And then you can spray your little sister or brother who's running away from you, trying not to get wet. So that's exactly what happens, and you all have experienced this. Saying it in nerd is saying the bigger the cross-sectional area, the slower the velocity. Now, at the same time, you can also say in nerd, the smaller the cross-sectional area, and I'm just going to call it cross-sectional area for, space's sake, the bigger, the greater the velocity. All right, and this is what we see in this example here. So back to this. If we have the same velocity, that must mean we have the same size. There is only two places, at W and at Z, where our pipe is the same size. All right, here we will be going a little bit, let's see here, When we make a smaller cross-sectional area, the greater the velocity. So here we'll go a little bit faster, and then finally, since this is the smallest part of the pipe, we'll be going the fastest here at Y. So the two places that we have the same size are at points W and Z. The reason they have the same velocity is because they have the same width, or cross-sectional area. Okay, so that is the answer for that one. Oops, sorry. And that is the reason for that one. So it's very important. Again, we're taking these two ideas and we're applying them to these situations. So that is how our width, or the size of our path, is going to affect our resistance. Here, we are looking at the zone W, X, Y, or Z that has the highest resistance. Because it's a question I'm asking you, I always want to know why. That said, let's go back up here to our ideas. The resistance depends on the shape of the path. We're going to need to go up a couple of slides. The shape, really sharp turns make it flow a lot slower. All right? When you are going slow, that means you have the highest resistance. All right? So an increase in resistance means you're slowing the flow. So our highest resistance is where we're going to have the lowest flow, and that is going to be at the sharpest turn. Okay? The only place we can pick is here in zone Y. And the reason is because it's the sharpest turn, and the resistance is greatest at the sharpest turn. The reason is because it's the sharpest turn and resistance where there are turns. Okay? Great. So we need to actually add these notes, and I'm going to go and I'm going to do that. We have them summarized here. This is really what you need to remember, is your size and shape will cause something to change with your resistance.